The research paper presents a novel quantum circuit for fault-tolerant T-gate implementation without probabilistic S-gate correction, which significantly reduces resource requirements and simplifies operations. This work is crucial for large-scale quantum computing applications, as it addresses the overhead associated with fault-tolerant quantum computation. The proposed circuit combines selective destination teleportation, selective source teleportation, and a fault-tolerant T-gate circuit to achieve accurate T-gate operation. The authors demonstrate that this approach can be improved by designing a circuit that directly performs a fault-tolerant T-gate without selective destination and source teleportation, resulting in a more efficient circuit. The proposed circuit, depicted in Figure 3, utilizes only two ancillary states, Y and A, requires two CNOT operations, and necessitates two measurements in either the X or Z basis. This leads to Theorem 1, which states that a quantum circuit to perform a T-gate without probabilistically applying the S-gate can be designed using a maximum of two ancillary qubits, two CNOTs, and two X or Z basis measurements. A comparison with the previous circuit, Table 1, reveals significant reductions in resources, including a 60% reduction in ancillary qubits, a 67% reduction in CNOTs, and a 60% reduction in measurements. The paper also presents a detailed analysis of the circuit operation, including the measurement outcomes and the corresponding operations. The authors show that the proposed circuit can be adapted for fault-tolerant T-gate implementation, as depicted in Figure 4, with a similar structure to the fault-tolerant T-gate implementation. This research contributes to the development of an efficient compiler for fault-tolerant quantum computation, enabling efficient time-optimal quantum computation. The proposed methodology for executing time-optimal quantum computation involves a circuit that can perform T-gates without applying S-gate correction probabilistically. This is achieved by using a quantum error-correcting code that enables universal fault-tolerant quantum computation and transversal measurement of logical X and Z. The time complexity of arbitrary quantum algorithm execution corresponds to the product of the number of layers consisting of independent T-gates and a single physical measurement time. Here is the combined summary of pages 58 of the research paper. The authors propose an efficient quantum circuit for fault-tolerant T-gate implementation without probabilistic S-gate correction, as shown in Figure 4. This circuit can be used for all fault-tolerant quantum computations, reducing the substantial time overhead previously thought to be required. A comparison with the previous known circuit for fault-tolerant, HT-N is presented, highlighting the proposed circuit's advantages. The proposed circuit consists of two N ancillary qubits, NCNOTs, NCZ gates, two Hadamard gates, and two NX or Z basis measurements, with a total depth of N+4 excluding X or Z gates based on measurement results. This achieves a 60% reduction in ancillary qubits, an 80% reduction in CNOTs, and a 60% reduction in measurements. The authors also apply their design to time-optimal quantum computation, as shown in Figure 6. The proposed circuit achieves a 40% reduction in ancillary qubits, a 50% reduction in CNOTs, and a 40% reduction in measurements, enabling time-optimal quantum computation with fewer resources. This leads to Corollary 1, which highlights the efficiency of the proposed design. By introducing a novel approach to fault-tolerant quantum computation, the authors focus on reducing resource consumption while maintaining time optimality. They decompose the controlled V-gate into two H-gates, four CNOTs, two T-gates, and one T-gate using an ancillary qubit, as illustrated in Figure 7. The H-gate is then converted into the initialization, NOT, and measurement, ICM, form, depicted in Figure 8, facilitating a versatile methodology for circuit optimization. The authors achieve a significant reduction in resources required for the implementation of the controlled V-gate, reducing the number of ancillary qubits by 41%, CNOT gates by 43%, and measurements by 43%. This reduction in resources enables the development of an efficient compiler for fault-tolerant quantum computation. The approach achieves a 60% reduction in resource requirements for a fault-tolerant T-gate without probabilistic S-gate correction, exhibiting a 60% reduction in ancillary qubits, a 67% reduction in CNOT gates, and a 60% reduction in measurements. The development of fault-tolerant quantum computation is crucial for achieving practical quantum computing, emphasizing the importance of error correction and fault tolerance, as demonstrated by Shor's work on fault-tolerant quantum computation with a constant error rate. The authors draw upon Gottesman's introduction to quantum error correction and fault-tolerant quantum computation, as well as Shenda et al.'s work on the synthesis of reversible logic circuits, a fundamental component of quantum computing. The paper explores the synthesis of depth-optimal quantum circuits using a meet-in-the-middle algorithm, and acknowledges Ross and Selinger's contributions to Onkila-Free-Clifford plus T approximation of zerotations. The authors also reference their own research on efficient decomposition methods for controlled Rn using a single ancillary qubit. The authors cite various studies, including Gorgio et al.'s work on T-count and T-depth of multi-qubit unitaries, Fowler's time-optimal quantum computation, and Babish et al.'s discussion on error-corrected quantum advantage beyond quadratic speedups. Additionally, they reference Chamberlain and Campbell's work on universal quantum computing with twist-free and temporally encoded lattice surgery. The paper also touches upon Hanks et al.'s effective compression of quantum-braided circuits aided by Zix calculus, Amy et al.'s polynomial time T-depth optimization of Clifford plus T circuits via matroid partitioning, and Paler et al.'s fault-tolerant high-level quantum circuits. Finally, the authors acknowledge Nielsen and Chuang's seminal work on quantum computation and quantum information, as well as Bravey and Kataev's universal quantum computation with ideal Clifford gates and noisy Onkelas, and Paler et al.'s regular representation of quantum circuits.